Angular velocity measures how quickly an object rotates around a central point. So you guys can think of maybe a dryer. All your clothes rotate around a center point, the middle of it. You can think of a yo-yo. As you spin a yo-yo, if you spin it in a circle, it's going around a central point. Angular velocity measures how quickly it does that, how quickly it rotates. Linear velocity goes in a straight line. That's why it says linear. And it's an object that travels, it's the distance that an object travels per unit of time in a given direction. So for example, linear velocity could be me walking a mile in 15 minutes. That's distance over time. If I want to call it velocity instead of speed, I need to add a direction to it. So maybe I do 1 mile, 15 minutes in the north direction, okay? When you add a direction to it, it becomes velocity instead of linear speed. Okay, so these are the equations you need to know. Angular velocity, remember, whenever we talk about angles, you can talk about it in 3 different ways. You can give me the degree, you can give me the radian, or you can give it to me in 1 revolution. Those are the 3 ways you can give me angles, okay? And this T stands for time. So this is how you find angular velocity. Linear velocity is the arc length over time. So for example, it could be 3 inches in 2 minutes. This can be 2.5 revolutions in 5 seconds, okay? Those are some examples of what they might look like. Now, we're going to be combining these 2 concepts in this equation here. When an object moves along an arc, you're going to have to combine both of these 2 things because an arc has an angle, and if you're moving along the angle, you're going to have a linear velocity. So we're going to be combining these 2 concepts. This R stands for radius, and your radius is distance over radians. Okay, we're going to use these 3 equations in an example. All right, so here's our first equation, our first problem. A bicycle's wheel, we'll pause there. Do you guys see how we're using both angular velocity and linear velocity? When you have a wheel, it's spinning. So if you make 1 full spin, that's 360 degrees, right? That's an angle. A bicycle is also moving forward. That's distance. So we're doing angular velocity because it's spinning, and it's also moving forward. That's linear velocity. So we're combining these 2 concepts. So we're going to be combining the concepts by using this formula. Linear velocity equals angular velocity times the radius. This is the formula here. What I have boxed. This combines your 2 concepts. This is not a W, this is the symbol omega. All right, so let's go ahead and solve this problem. A bicycle's wheel has a 30-inch diameter. Okay, this stands for the radius. So what is my radius? 15 inches. The diameter is 30. That means the radius is 15 inches. So I'm going to put 15 inches into my formula. Okay, if the wheel makes 1.5 revolutions per second, so let me write that down. Remember, let's look at the notes. You need to put the angle over time. You can either use revolutions, which is what our problem did, radians, or degrees. So we're going to use revolutions over time. They said it's 1.5 revolutions per second. So I'm going to substitute my omega with that. 1.5 revolutions per second. And I need to solve for linear velocity, v. Okay, so go ahead and use your calculator. What is 1.5 revs, or what's 1.5 times 15? What is it? 22.5. And I have 2 different things. I have revs and I have inches. We're gonna need to get rid of some things. Because look, it says I want my answer in miles per hour. This is definitely not what I have. I have revs times inches over seconds. I do not have miles per hour. Okay, so we need to convert this answer. So what I'm going to do, first of all, I don't want revs. So if I want to get rid of revs, revs needs to go on the bottom. One rev is what? It is 360 degrees, but I don't want degrees either. So what should I put? 2 pi. Great, that's just a number. So my revs are gone. I also need to get rid of inches because I want miles. This stands for miles per hour, MPR. So I need to get rid of inches. So inches will go on the bottom. There's 12 inches in 1 foot. I'm still not at miles. Do you guys remember from yesterday how many feet are in a mile? Exactly, 5,280. Okay, now I got to my miles. That's great. The feet cancel out. We're still not there. We have seconds right here, but my desired unit is hours. So I need to get rid of seconds. I'm going to put seconds on top. Well, do you know how many seconds are in 1 hour? Exactly, 3,600. Perfect. So seconds cancels out with this seconds. Now I am in my desired unit. The only unit on top that is left, that's gone. That's gone, that's gone. The only thing left is miles. So I'll have miles on top and hours on the bottom. That's the only unit that's left, miles per hour. Now, go ahead and grab your calculator, please. We're going to calculate what this is. I'll grab one too. So in your calculator, type in 22.5 times 2 times, hit your pi button, times 3,600. Enter. That's all of the numerator. Now, divide, hit the division button. Divide by 12, hit enter. Divide by 5,280, hit enter. You should have gotten 8.028 miles per hour. The pilots are traveling at 400 miles per hour, and the circular room has a radius of 25 feet. So remember our equation. Linear velocity is equal to angular velocity times your radius. And it wants us to find the number of rotations that it makes per second. So I'm wanting rotations. Another word for rotations is revolutions per second. That's the unit that we want to end in. Okay, really quick, the 400. Does that go here or here? Raise your hand if you think it goes here. Raise your hand if you think it goes for the V. Yes, that's correct. Remember, this is angular velocity. They didn't give me any type of angle. They gave me miles. That's linear, that's distance, okay? They gave me miles. So that needs to go for the velocity, for V. So I'm gonna put 400 miles per hour for my linear velocity. My radius is 25 feet, so I'll replace that. And we want to solve for omega. So what I'm going to do first, go ahead and divide this by 25 feet. That cancels out. Divide this side by 25 feet. I'm going to do something that might help you visually. You can put this over 1 And remember, whenever you're dividing fractions, you flip the second one and multiply. So this is 400 miles per hour times, you're going to flip this. So now the 1 is on top. The 25 feet is in the denominator. And this is equal to omega. So I'll just put it on this side. Okay. Now, guys, we need to make sure we get it in revolutions per second. Let's put our answer in revolutions per second. Okay. First off, I know I don't want miles. So I'm going to put miles on the bottom. And I don't want feet. I'll put feet on top. So 1 mile is 5,280 feet. Feet cancels out with feet. Miles cancels out with miles. Okay. I don't want hours. I want seconds. So I'm going to multiply by putting hours on top. How many seconds are in an hour? Exactly 3,600 is in 1 hour. So notice hours cancels out with hours. Am I done? Did I get to my units? Is there revs anywhere in the numerator? No, I don't have revs yet, so we need to add a rev. So I'm going to multiply by 1 rev. And how much is 1 rev? 2 pi. Do not put 360 degrees because we don't want degrees. So put 2 pi. Perfect. So I have all of my units that I want. The only thing in the numerator is rev, and the only thing in the denominator is seconds. That's the unit that I wanted. Now we're going to multiply everything on the top and divide by everything in the denominator. Your answer is 3.735 revs per second. So our next problem, we have a clock. And the second hand is going around the clock. It ticks. It goes around the clock. And it travels at 2.5 inches per second. Inches, that is distance. That is your velocity. So that is 2 for your formula. This is our formula. That'll be 2.5 inches per second. Equals. You need to think about what angular velocity will be, and we need to figure out the radius. This, you can figure this out by reading the problem and thinking about it. You're given a clock. You know it's the second hand. It goes tick tock tick, right? Figure out what you should put for this omega. I'm going to pause here. So remember, in order to find angular velocity, the formula is the angle measurement over time. So if you have a full circle, a clock, the angle measurement is 2 pi. So I know my angle measurement for a clock is 2 pi, since that's a full circle. Now the time it takes a second's hand to get around the clock is 60 seconds. So this is what you should put for omega. Now that we have our variables filled out, we can solve for r. So what I'm going to do is divide by 2 pi over 60 seconds. That cancels out. Divide this side by 2 pi over 60 seconds. Okay, so what I have now is 2.5 inches over seconds times 60 seconds over 2 pi. Because you flip this second one and you multiply it. So the seconds will cancel out with the seconds. So plug this into your calculator. This is 2.5 times 60 divided by 2 and divided by pi. You guys should get your units seconds. Oh, sorry. We canceled out seconds. The units that are left over are inches, which makes sense because it's length. So let me know what you guys got. 23.873. Perfect. So that is how long this seconds hands is. Two gears are connected by a belt. Let me draw you a picture so you can visualize what's happening. Here's a gear and here's a larger gear, and it's connected by a belt. Think of like a bicycle chain. It just rotates around these two gears. The small one has a radius of 3 inches, and the larger gear has a radius of 6 inches. Okay. If a point on the small gear travels at 16 revolutions per minute, let's just pause here. The key word is revolutions. So in my formula, will it represent the V or the omega? Which one, V or omega? Omega, because remember, this is your angular measure. Angles are in revolutions, radians, degrees. Okay. So they just gave me the angular velocity for the small gear. Find the angular velocity of the large gear. So this is the angular velocity of the smaller gear, because remember, it's revolutions over time. That's angular velocity. So there's a 16 over a minute. Okay, so let's plug it into the formula here. I know that the velocity, I'm just going to say S for the small one. So for the small one, the angular velocity is 16 revolutions per minute times the radius, which is 3 inches. That is all the information they gave me for this small gear. Okay, now let's talk about this large gear. The large gear, the velocity of the large gear is going to be angular velocity times the radius, which is 6 inches. Okay, now I'm going to pause here and let's talk about my picture. I'm going to use blue. This point is going to travel around the small gear, and then it's going to travel along the big gear. Isn't the speed at which it moves consistent? Yep, it's going to be consistent. Just because this is a smaller gear doesn't mean it's going to speed up or slow down. This point is just going to rotate. If you ever see a bicycle wheel or something like that, or the gears, they just move at the same speed, okay? So that means the velocity here is the same as the velocity here. What is different, though, is the angular velocity, okay? It's going to take a much longer time for it to rotate around here, for this to rotate, than for this to rotate. That'll rotate pretty fast. But the points along the outside on the belt, it's a consistent speed. So your velocities, your linear velocities are the same. Okay? Your linear velocities are the same. What I'm saying is the velocity here is the same as the velocity here. Okay? Your linear velocities are the same. Okay. Now look. I know the linear velocity here is this. So I'm going to put that here. 16 revs times 3 inches over minutes. That's what the linear velocity is for the small one. It's also going to be the same thing for the big one. Now we have everything. We can solve for our angular velocity, omega. So what I'm going to do to both sides is divide by 6 inches, divide by 6 inches, and I'll put it over 1 so you can visualize it better. So I have 16 revs times 3 inches over minutes times 1 over 6 inches equals omega. And wonderful, that cancels out. So if you multiply across, 16 times 3 times 1 is 48 revs over 6 minutes. What's 48 divided by 6? So this is 8 revs per minute. That's it. If you want to, you can still write it as this, 8 revs per minute. And remember, it makes sense because omega is always your theta angular, your theta, which stands for your angular measure, and minutes. And we have 8 revolutions per minute.